Hello everyone, we are Group 45 and today we are presenting on a paper titled Bridging Legal Knowledge and AI Retrieval-Augmented Generation with Vector Stores, Knowledge Graphs and Hierarchical Non-Negative Matrix Factorization. This paper was presented at ICAIL 2025. We are excited to walk through its core ideas and contributions to the intersection of AI and law. This paper was presented at International Conference on Artificial Intelligence and Law (ICAL) held from 16 to 20, 2024 in Chicago. It was authored by Ryan C. Barron, Maxim E. Iran, Olga M. Serafimova, Cynthia Matsuzek, Boyan Alexandrov. Legal systems are highly complex and deeply interrelated. Traditional keyword-based search systems often fail to grasp the contextual and semantic nuances of legal documents. This poses a challenge for legal professionals who need precise and relevant information to address this. The paper explores how AI, specifically generative models, can understand legal content in the context not just through keywords but through deeper semantic reason. The main objective of the paper is to propose a new generative AI system that enhances legal document analysis. It integrates four main components: Retrieval-Augmented Generation or RAG, vector stores for storing semantic embeddings, knowledge graphs to represent structured legal knowledge, and non-negative matrix factorizations to uncover latent legal topics. Together, these tools aims to improve the interpretability and reliability of legal AI systems. What is augmented generation? Retrieval-Augmented Generation or RAG combines two key tasks: retrieving relevant legal documents and generating informed, context-aware responses. Unlike traditional large language models that may hallucinate or fabricate facts, RAG grounds its output in real legal text. This approach is particularly valuable in tasks such as summarizing case law, answering legal questions, or finding relevant precedents, ensuring greater accuracy and reliability.
Okay, now let's explore vector stores and their role in this system. A vector store is a special kind of a database that stores documents as numerical embeddings, capturing the meaning of the text. In this paper, the authors used OpenAI embedding model to convert statutes, case law, and constitutional provisions into vectors. So they are using OpenAI to vectorize the words into the embeddings. So these vectors go beyond keyword matches. They understand the concept and the context as well. So to store and retrieve these vectors and having a system that create vectors and also having a system that retrieve vectors when we want, they're using Milvus, a high performance vector database. So when a legal question is asked, the system doesn't search for keywords. It looks a semantic similar fragments using these embeddings. So this is called the vector search. When you search a when you search a vector, it gives you not that specific vector, it gives you the vectors relevant that vectors using the semantic similarity, using the embeddings. So this drastically improves the legal search, especially for vague or abstract queries. Let's move into the next slide, modeling law with knowledge graphs. Next, we have the knowledge graphs. The legal knowledge is just not the text. It is highly relational, right? For instance, a statute might be cite another law or case might be interpret a constitutional clause. So this paper uses a Neo4j based knowledge graph to model these relationships. Each node in the graph represents a legal entity like a case, statute, or a topic, and edges represents the relationships such as cites, override, or discusses. The structure makes it possible to trace how legal ideas connect. For example, if you want to know all cases discussing specific law under a topic called estoppel, which is a New Mexican law word. When it comes to this word is used by a New Mexican a law which is this research paper is based, knowledge graph is enables that. It adds explainability and traceability to the AI system, which is more crucial when it comes to the law-based AI systems. Let's move into the next slide. Non-negative matrix factorization, also NMF. Now let's talk about how the system understands the structure of the legal content using a simple technique called NMF. NMF is a topic modeling method that breaks down documents into a mixture of interpretable topics based on term frequencies. Term frequencies. In this paper, the authors use TF-IDF, term frequency inverse density framework, vectors for cosine similarity to group legal clauses and section into meaningful topics. These topics were organized hierarchically. For example, the Constitution was clustered into 10 major themes. This method helps uncover legal themes like contract law or estoppel across different document types. The NMF topics were also added as nodes in the knowledge graph, further enriching the network of legal meaning.
Thank you, Nisal. So let's see what are the data collection methodologies. The author gathered legal text from JustDR, a public platform that provides access to US legal documents like states, court rulings, and the constitutions. To ensure ethical and responsible access, they implemented the web scraping with strict rate limits and activity logging. From these documents, they extracted structured legal information. This includes metadata such as titles, decision dates, and court names. They also captured content like stationery text and legal citations. What is important to highlight is that this data was collected slowly per academic non-commercial research. The process strictly compiled with just the term of use ensure no misuse or overloading of their platform. So let's move on to the next slide. So legal text processing. Once the legal data was collected, the next step was to process it in a meaningful way. To identify legal themes and group similar content, the author used a combination of TF, IDF, and non-negative matrix factorization, or IMF. These methods allow them to automatically form topic clusters such as those related torts, contracts, and constitutional rights. They also applied hierarchical decomposition, breaking down large legal documents into sections and even individual clauses. This allowed for details analysis at multiple levels of legal structure. To improve interpretability, they use GPT-4 to generate automatic topics like these AI-generated labels help to quickly identify the purpose and scope of each cluster, reducing the need for manual curation. So let's move on to the next slide. So a key innovation of the paper is the legal knowledge graph built using Neo4j. In this graph, each node represents a legal component such as date and constitution sections or court case. The connection or edges represent relationships like citations or shared legal topics based on earlier clustering. The team also integrated NMF keyword data into a graph, allowing more complex semantic connection to be visualized. A great example is the large concept of exponential, which can appear in multiple documents across states and case law. The knowledge graph links these instances together, giving a user visual map of how a legal concept is discussed and applied across different sources. So let's say, on to the next slide. In here, we are going to talk about what is the vector store architecture here. To support smart, efficient legal search, the author used Weakfluence, a high-performance vector database. All legal documents were embedded into vector format using OpenAI language models and these vectors allow the system to perform semantic search returning results that match the meaning of query, not just the exact words. The documents were indexed into three separate categories like constitution, states, and case law. This improved accuracy and speed during retrieval. When the user submits a question, the system fetches the most relevant legal passages and provides metadata like the document title and direct source link. This ensures that user can verify the legal content and explore the original text if needed. So, Piruna can continue the presentation.
Thank you, Kadu. Now let's look at how the system helps a typical legal query. The query flows with the user submitting a question. The question is first processed by the retrieval-augmented generation model. From there, it searches the vector store, which holds symmetrically indexed legal documents. Relevant documents are then passed into the knowledge graph. This combined context is finally given to the language model. The strength of this pipeline is that it produces responses grounded in actual legal text, and because each step is traceable, the user can go back and verify the sources, something especially important in legal research. In the next slide, in terms of the performance, the system shows impressive results when applied to legal data from the state of New Mexico. Using non-negative metrics for factorizing, the legal corpus was organized into hierarchical topic clusters. The constitution was grouped into 10 distinct clusters, statutory law into 198 clusters, Court of Appeal case into 420 clusters, and Supreme Court cases into 248 clusters. These groupings allows for easier navigation to the legal corpus, pattern discovery, and topic-based search. Let's move on to the next slide. To benchmark the system effectiveness, the authors compared it against several well-known large language models, it including GPT-4, Gemini, Smartstick, and Immortal. They assess two key metrics. They are attempt rate, which measures how often model tries to answer a legal question, and accuracy, which evaluates how often the answer is actually correct. The proposed system consistently outperformed the others. Its combination of semantic search, structured reasoning, and retrieval grounding helped in generated more reliable and domain-approached answers, particularly valuable in legal contexts where precision matters. In the next slide, to sum up, the paper introduces the cutting-edge legal AI framework that successfully blends semantic, structural, and later knowledge techniques. The authors demonstrate a system that is both scalable and practical for real-world legal document analysis. Most importantly, this work shows how AI can bridge the gap between raw legal and data meaningful, explaining insight, making legal research faster, smarter, and more reliable. Finally, before we wrap up, we had like to acknowledge the authors to their significant contribution and computational legal research. Thank you for all your time and attention.